In our last video, we learned a little about what we can see in our night sky, as well as the two models of our universe. The geocentric model was where Ptolemy incorrectly placed Earth at the center of everything. The heliocentric model as Copernicus properly placed the Sun in the center of our solar system, with planets including Earth orbiting around it. You should remember that Galileo used his telescope to find numerous examples of evidence that supports the Copernican model. Now we will be taking a look at how observations made by Tycho Brahe led to Kepler's laws of planetary motion that further support the heliocentric model. In this photograph we see evidence of Earth's rotation. A long exposure was taken using a camera aimed at Polaris, our North Star. As Earth rotates, stars appear to orbit Polaris, but what is actually happening here as the Earth is rotating? Our axis points at Polaris, so as Earth rotates, objects in the sky appear to go around our pole star. They are actually stationary, or not moving. The glow behind the mountains is the northern lights. Venus exhibits what is called retrograde rotation. It may have suffered an immense collision with another planet-sized object early in its history and gotten knocked completely over. The Sun would rise in the west and set in the east on Venus. All of the planets, except Venus, rotate counterclockwise. Any appearance of motion caused by the rotation of the Earth is called an apparent motion. They include the rising and setting of the Sun, the Moon, the planets, and most of the stars. Some stars appear to circle around Polaris, as mentioned on a previous slide. These stars are part of what are called circumpolar constellations. They appear to circle the North Star and include Ursa Major and Ursa Minor, Cassiopeia, and Draco, to name a few. In Greek mythology, Helios carried the Sun across the sky each day in a golden chariot. Today we know that the Sun only appears to rise and set due to Earth's rotation. It is an example of an apparent motion. As the Earth rotates from west to east, objects in the sky, Sun, Moon and planets, appear to move westward. This makes them appear to rise in the east and set in the west. Mars is one planet that exhibits a complex behavior that required Ptolemy to come up with his deferents and epicycles. A simpler explanation is that Earth is closer to the Sun than Mars, so catches, and then passes, Mars as both planets orbit the Sun. As we catch up with the red planet, it appears to slow down and stop. When we pass it, Mars begins to appear to move backward. Time-lapse photographs of Mars show it tracing what is called a retrograde loop as we catch and pass the planet. The Moon orbits Earth once every 27.5 days. So, in one day, the Moon moves about 13 degrees of its complete 360-degree orbit. The Earth rotates through 15 degrees each hour. 13 degrees is about 50 minutes, so the Moon rises 50 minutes later each night. Before you continue watching this video, pause and complete the Moon phase dial activity. Directions are found on Google Classroom. There is also a Google Doc assigned to you to answer questions as you learn to use the Moon phase dial. As Earth orbits the Sun, different constellation will appear in our night sky. At the summer solstice, Aquarius, Capricorn, and Sagittarius will be visible in the evening sky. Past and future positions of the Earth show that over time, the solstices and equinoxes move through the zodiac. This motion is very slow, and would take 26,000 years for the Sun to move from its current position in the zodiac and back again. This motion is called precession. It is basically the Earth wobbling on its axis, completing one wobble every 26,000 years. Ptolemy's geocentric model of the universe was very complex, requiring equants, deferents, and epicycles to explain most of the observed motions of objects in the sky. Copernicus's heliocentric model is much simpler at explaining all of these things. Tycho Brahe was a Danish astronomer who was supported by the King of Denmark. He made many detailed observations of the position of stars and planets. Johann Kepler worked with him, and developed a series of mathematical relationships that explained, and predicted, the motion of planets. In his observatory at Uraniborg, Brahe used devices such as sextants to mark the changes in position of the planets. He did not use telescopes. Kepler's first law is that planets move in paths known as ellipses, not circles. This was a departure from the Copernican view that planets moved around the Sun in circular orbits, a holdover from an early idea that the heavens were a perfect creation and circles are a perfect geometric shape, so therefore their planets' orbits had to be circular. The further apart the foci of an ellipse are, the more eccentric the orbit is. In an elliptical orbit, the Sun is at one of the foci. Planets generally have a low eccentricity. Many comets have a high eccentricity. Pause the video and complete the elliptical orbits activity. There is a Google Doc assigned to you on Google Classroom to answer question about what you are learning here about planetary orbits. Directions for the activity are also given. Kepler's second law is also known as the equal area law. Planets move fastest in their orbits when they are closest to the Sun, due to the increase in the Sun's gravitational attraction as they approach closer. As they move away, this force decreases, so does their speed. Looking at the diagram on this slide, T1 is time 1, T2 is time 2. They are the same, even though the length of the orbital path at both locations is different. This is again due to the difference in speed that the planet is traveling at each location. S1 and S2 are the area swept by the planet at that location. Again, these areas are equal. In the formula shown here, P stands for the period of a planet. Period is the time it takes for the planet to complete one orbit. All objects orbiting another object have an orbital period, not just planets. Earth's orbital period around the Sun is 365 1/4 days. Remember, on a previous slide you learned that the Moon's orbital period around the Earth is 27 1/2 days. A in the formula stands for distance from the Sun. This distance is in a unit known as an astronomical unit. An astronomical unit is the average distance from the Earth to the Sun, or 93 million miles. In metric units, this is 150 million kilometers. Use the formula given on the previous slide to calculate what is missing for each planet. Send me your answers on a brief email.